Hello students, myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, I am going to teach you TE modes in a rectangular waveguide. So before on going through the basic description about the TE modes in the rectangular waveguide, just for the recap for you, what is meant by the TE mode? The TE mode stand for the transverse electric. And if you are recalling it, transverse electric means the electric field component will be equal to 0 in the direction of the wave propagation. That means, if we are assuming that the wave is propagating in the z direction, then the electric field component in the z direction should be equal to 0. That is, Ez component should be equal to 0 in the case of a TE mode. Now, let us have a look at the rectangular waveguide. This is a rectangular waveguide having a dimension of A cross B, and always we are assuming that A is greater than B here. So, this is the dimension and the wave is propagating in the z direction. So, this is the minus z and this will be the plus z, and this is our rectangular waveguide. A is in the x direction, B is in the y direction, and the dimension where wave is propagating. Now, we will start with our description of the TE modes. That means, in here we will calculate the electric field and the magnetic field components, all the electric and the magnetic field components which exist in the rectangular waveguide for a TE mode. So, when we talk about the electric field and magnetic field component, that means we are going to calculate Ex, what will the value of Ex, what will be the value of Ey, what will be the value of Ez. Of course, we know the value of Ez here. For the TE mode, it is equal to 0. And what is the value of Hx, what is the value of Hy, and what will the value of Hz. So, in roundup, we can say that we are going to calculate the 6 component of the electric and the magnetic field in the TE mode, where Ez equal to 0. So, the main component of which we can derive first of all is with the help of our wave equation. And what is our wave equation? And the first question arises in your mind that why we are writing here the wave equation in the terms of H. Wave equation can be written in the terms of both E and H. For example, when we write it in the terms of E, this will be del square E is equal to gamma square E. And if you are able to recall it, this gamma is our propagation constant, which is equal to alpha plus j beta. Alpha is our attenuation constant and beta is our phase shift. So, why we are writing this electric field component in the terms of magnetic field? Because here in the direction in which the wave is propagating, our electric field component is 0. Already I have told you that for the TE mode, Ez equal to 0. So, the component which is existing in the direction of wave propagation is the magnetic field only, and that component is the Hz. So, the wave equation which is written here is in the terms of the magnetic field, and that is also the Z component. Del square Hz should be equal to gamma square Hz. And already in the last class, we have calculated the solution of this wave equation, and that comes to be like this. When we write it in the terms of magnetic field, it is like this: Am, it is a constant, sine m pi x by A, Bm cos m pi x by A, Cn sine n pi by B plus Dn cos n pi by B. So, these are the basically constant which varies as per the boundary condition. So, what you always try to remember that Am, Bm, Cn and Dn varies as per the boundary conditions. and this is A, these are the dimensions of the waveguide, depends upon the dimensions of the waveguide A and the B. And when we say M and the N, that depends upon the number of half wavelength in the x direction and the number of half wavelength in the y direction. About this we have already studied in the last lecture, but today just I am recapping it. So, as per the boundary condition also, Kx, normally we used to write it as Am sin Kx x. So, this Kx is m pi by A, and this is our Ky, which is equal to n pi by B, and this is also as per the boundary condition, that is as per the waveguide available with us, and this is a rectangular waveguide, that is why Kx is equal to m pi by A and Ky is equal to n pi by B. Now, we have just from this equations, from this wave equation, what we have derived? We have calculated the value of Hz only. So, we have to calculate Ex, Ey, Hx, Hy. So, the first value Hz is now with us. We have to just calculate the value of Am, Bm, Cn and Dn, but a rough value is available with us. So, for calculating the rest of the expression in relation to, we have now available with the Hz value. So, we have to get the expression of Ex, Ey, Hx, Hy in the terms of Hz. So, the basic things, basic calculation which I am going to do right here is just to get the expression of this 4 in the terms of Hz. So, for that I am writing the Maxwell curl equation. Del square E is equal to minus j omega mu h, del square h is equal to j omega epsilon E. These are the two curl equation of the Maxwell. So, what we have to write? We just, for the simplicity, you can write it as like this: Ax, Ay, Az. I am writing the expression of this one. So, when you write in the terms of this, and first of all, and this is in the upper side and this will be on the lower side. By solving it, what we will able to get is the expression of this. I am just going to solve it for you. So, the first expression Ax cap is equal to del by del y Ez minus del by del z Ey. So, you are able to see that we are getting this expression, and when we break down this j omega mu Hx Ax cap plus Hy Ay cap plus Hz Az cap. So, the x component minus j omega mu Hx. So, in this way we can have the expression of all this, and when we want this value, so this way Ay component minus j omega mu Hy. This was Ay component, and this was the Az components minus j omega mu Hz. And for calculating the Ay component, we will write like this: minus Ay del by del x Ez minus del by del z Ex. So, you are able to see del upon del z Ex, this will be a positive sign, and next one minus del upon del x Ez. And similarly, you can have the value of Hz. And for calculating the terms in the form of a Hz, so what we have to do? We have to write again del cross H. And this will be equal to j omega epsilon Ex Ax cap plus Ey Ay cap plus Ez cap. Now get the Ax component. What we have? Del by del y Hz minus del by del z Hy, and this is equal to what component? Ax component in the RHS side, and this is equal to j omega epsilon E. Or if you are able to see it, this expression, see this expression, this is exactly the same, del upon del y Hz, del upon del z Hy, and in the RHS side j omega epsilon Ex. Similarly, you can have the value of Ay, Az and equate this with the Ay cap and Az cap component of the RHS, and you will able to get this expression and this expression. So, before proceeding forward, you just solve it that you are getting this equation or not. These steps are already known to you, that how to solve it. Now, we have got that 6 equations. Now, what the second step we are doing? That we are substituting del upon del z with minus j beta g, and Ez already known to you, that is a TE mode, that is why Ez should be equal to 0. So, just take the first component, this expression, first expression, and if you are substituting del upon del z by minus j beta g, okay. So, minus j beta g and Ez equal to 0. So, what you are getting? If you are taking this Ez equal to 0, the first term, then this will be equal to 0 minus, at the place of del upon del z, you can substitute minus j beta g. So, minus minus, this will be plus j beta g is equal to minus j omega mu Hx. So, if you are able to see the expression, first expression, this is exactly the same one, yes or no? This is exactly the same one. Similarly, by substitution of the second expression, what we are getting? Now, the second one, del by del z is replaced with minus j beta g Ex, Ez equal to 0, that means this will be equal to 0, minus j omega mu Hy, minus minus cancel out, z cancel out, beta g Ex is equal to omega mu Hy. So, here is your beta g Ex omega mu Hy. So, you can get the all this expression, first two I have done for you, and the rest of you can have it by just by substituting del upon del z by minus j beta g and Ez equal to 0. So, all of you are instructed to just substitute in all the expression, for example, third, fourth, fifth and sixth, the expression del upon del z is equal to minus j beta g and Ez equal to 0. You are able to get this expression, and this expression are in the same order as in the previous section. So, we are able to get this expression. Now, as I have told you that our wave is propagating in the z direction, and the only filled component which are known to us, that is our hz. Ez is equal to 0 and the wave is propagating in the z direction. So, with the help of wave equation, we are able to get the expression of hz, and since the wave is not propagating in any other direction, so we are not able to get the other expression from the wave equation. So, we have to write the expression of Ex, Ey, Hx, Hy all in the terms of Hz. So, if you are able to see this expression, so first of all, what we have to find out? We have to find out the value of Ex. So, in which expression we have Ex? We have Ex in this one, and in the other expression you are able to see, we have Ex in this one. So, with the help of, if we number it, this is 1, 2, 3, 4, 5 and this is 6. So, if we are able to get number it, so we, with the help of equation 2 and 4, we are able to find out the value of Ex and Hy in the terms of course, our Hz. This is the basic function we have. So, now equation 2, from equation 2, what we have? Ex is equal to omega mu upon beta g Hy. Are you able to get this? Ex is equal to omega mu upon beta g Hy. So, now substitute this expression of Ex into the equation 4. So, on substitution, what we are getting? Plus j beta g Hy is equal to j omega epsilon, and at the place of Ex you can write this expression. So, this will be omega mu upon beta g Hy. So, what we have? Del upon del z Hz and plus j beta g Hy is equal to j omega square mu epsilon upon beta g Hy. This is the expression available with us. Now, Hy is, if we take the Hy common, then this will be j omega square mu epsilon upon beta g minus j beta g is equal to del upon del z Hz. I am just doing nothing, just I am replacing the value. Now Hy, we can take j also common, omega square mu epsilon, omega square mu epsilon, and what you have? Beta g square, and denominator also beta g is equal to del upon del z Hz. And now we are able to get this expression. So, just what we are calculating? We are actually calculating the Hy in the terms of Hz. So, we have available with Hy, and in the next expression omega square mu epsilon minus beta g square is replaced with Kc square. Omega square mu epsilon minus beta g square is replaced with Kc square. So, what we have? Hy j Kc square by beta g square is equal to del upon del z del upon, yeah, this is y here, we have to correct it, del upon del y hz. So, are you not able to get this expression now? So, is now available with the expression of hy. So, we know that Ex is equal to omega mu beta g hy, omega mu beta g hy. So, Ex is equal to omega mu beta g hy. So, we can have the expression of this one here, now you are able to see that we are able to get this expression on solving. Jg beta g cancel, minus j omega mu upon kc square. So, now we are available with the Ex and hy in the terms of Hz. Similarly, if we want to calculate, now hy and Ex are with us in the terms of Hz. Now, we are have to calculate Ey and Hx. So, Ey and Hx are available in our equation 1, 2, 3, 4, 5. So, on solving equation this. So, on solving this two equation, we are able to equation 5, equation 1 and 5, we are able to get the expression of Ey and Hx in the terms of Hz. So, the steps are same as we have done for the calculation of Ex and hy. You should proceed in the same manner and you are able to get the expression. And always try to remember that omega square mu epsilon minus beta g square is equal to kc square. So, replace it and you are able to get this, and this is Hz is also already available with us. Now we are going to apply the boundary condition for getting the value of Hz. Now, we know that the tangent E field or the normal H field vanished at the surface of the conductor. So, we are having the boundary condition Ex is equal to 0 and del Hz del y is equal to 0 at y equal to 0 and b. So, if we are assuming the condition for y equal to 0 and del Hz upon del y, that is differentiation of Hz with respect to del y is equal to 0. So, we are going to differentiate the Hz component which is available with us, and what is our Hz component? This is our Hz component. So, differentiate it, you will get Am. We have to differentiate it in the terms of y. So, this Am sine, the sine terms which is the function of x is always treated as a constant, and e to the power minus j beta gz is already is also a constant. So, the only differentiation is done of Cn sine, the sine will change into the cos, and in the you will have the n pi by b also, dn n pi by b minus sine n pi y by b. So, this is the value we are getting. X function constant, z function constant, we are differentiating the only the y. So, here the Cn will be the equal to 0. Now, applying the second boundary condition where Ey is equal to 0, del Hz, del x is equal to 0 at 0 and a. So, on differentiation on the same basis, we are able to get the value of Am is equal to 0. So, this is our expression of Hz by taking Cn is equal to 0 and Am equal to 0. So, what will be the next step we are going to do? We are just substituting these values of Hz in the expression, because already we have derived the expression in the terms of Hz. So, we are going to substitute in this expression, Hz expression, and the second thing which we are going, the all constant we are substituting, and after that what we are doing, treating all constant with a single term, we are able to get this expression of electric field and the magnetic field components of our rectangular waveguide. So, this is the 6th expression of the electric field and magnetic field components in the TE mode of a rectangular waveguide. Thank you very much for attending the lecture.